Welcome to The Explainer. Today we're putting on our detective hats. We're going to find out how data analysts uncover and prove those hidden connections that are all around us, using a pretty powerful toolkit of statistical clues.
All right, let's dive right in with our first case. We are investigating a top business school where a pretty serious accusation has been made: gender bias in their admissions process. So, the big question is, does the data actually back up the claim?
So a women's forum looked at the raw numbers and pointed to what they saw as really clear discrimination. The school, though, they pushed back. They argued that, hey, the difference is just because we have a much bigger pool of male applicants to start with.
Okay, so this is our first piece of evidence. And, at first glance, these numbers look pretty stark. 288 men got an offer compared to only 36 women. But as good data detectives, we know we have to look deeper than just the surface, right?
So how do we dig deeper? Well, our first tool is something called conditional probability. You should think of it like a magnifying glass. It lets us stop looking at the whole, big picture, and instead zoom in on a very specific part of it to ask a much smarter question.
So instead of asking, what's the overall admission rate for everybody, conditional probability lets us ask something more specific, like, what's the probability of getting an offer given that the applicant is a man? And then, of course, we can ask the same thing for female applicants. It's all about adding that one little condition.
And wow, when we do that, the clue becomes crystal clear. We see that a shortlisted male candidate had a 30% chance of getting in, but a shortlisted female candidate, her chance was only 15%. That difference is suddenly way more obvious.
So here's the bottom line. A male applicant was literally twice as likely to get an offer as a female applicant. Now, does this single-handedly prove bias from just this one sample? Not definitively, but it provides incredibly powerful statistical support for the argument. The initial clue is, well, very strong.
Okay, but in any investigation, new evidence comes to light, right? So what happens to our beliefs when we get new information? How do we, update our suspicions as we go?
This is where a fantastic tool called Bayes' rule comes into play. It's basically a mathematical way of doing what great detectives do instinctively. They adjust their theories as new clues pop up. It tells us how to formally change our minds based on data, moving from an initial belief, which we call a prior, to a new updated belief, a posterior.
Let's see how it works. So, imagine a manufacturer gets parts from two different suppliers. Initially, their belief, their prior, is that most of their parts come from supplier 1, because S1 handles 65% of their business. Makes sense.
But then a new clue appears. An inspector finds a defective part. And we've got some background info here. We know that supplier 2, even though they're smaller, has a much higher defect rate. We're talking 5% compared to just 2% for supplier 1. So how should this new piece of evidence change our suspicion?
And check this out. This shows the power of Bayes' rule perfectly. After finding that one single bad part, our belief completely flips. The probability that the defective part came from supplier 2 jumps from just 35% all the way up to over 57%. We've updated our belief with evidence, and suddenly S2 is our prime suspect.
So, finding clues and updating our suspicions based on the data we have, that's one thing. But what if we want to make a really definitive conclusion about the entire population? Well, for that, we need to take our case to a kind of statistical trial.
So for this trial, let's look at a new case. A survey was done on brand preference in two cities, Mumbai and Chennai. We want to know, is there a real, genuine relationship between the city someone lives in and the brand they prefer? Or are the little differences we see in our survey just kind of random noise?
The courtroom for this trial is called the chi-square test of independence. This is the formal procedure we use to decide if two things, like city and brand preference, are truly independent of each other, or if there's a real association going on between them.
And what's really cool is how this breaks down a kind of complicated test into a super clear, logical process. We start by assuming there's no connection. That's called our null hypothesis. Then we calculate what the numbers should look like if that were true. Finally, we compare that to what we actually saw and decide if our initial assumption was just plain wrong.
So, the heart of this entire test is basically a showdown. It's a direct comparison between the facts on the ground, the actual survey numbers we observed, and this theoretical world where the two things have absolutely nothing to do with each other. That's our expected frequencies. The bigger the gap between those two, the more likely there's a real connection.
So the test boils this whole showdown into one single number. Think of it as a gap score. For our brand preference data, that score is 7.009. But is that a big number? Is that gap big enough to actually matter?
And the verdict is in. In any statistical trial, there's a threshold for evidence, right? A line you have to cross. For our test, that line was 599. Since our calculated value of 7.009 is bigger than that, the gap is just too big to be random chance. We reject our initial assumption, and we conclude, yes, brand preference and city are connected.
So, after all that detective work, what's the big takeaway from our investigation? What have we really learned here?
We've built this incredibly powerful three-part toolkit. We start by finding clues with conditional probability. Then we update our hunches with new evidence using Bayes' rule. And finally, we take our case to court with the chi-squared test to get a definitive verdict. It's a complete framework for going from just a simple hunch to a real evidence-based conclusion.
See, by learning to think like a data detective, you're not just consuming information anymore. You're now equipped to question it, to test it, and to find the true story that's hiding just beneath the surface. So, go find those connections.